Okay, so moving on to page 2 of our notes, section 11.1, sequences and series. The sum of a sequence is called a series, which we kind of talked about on page 1. We will often write a series using what we call a summation notation, or often referred to as a sigma notation. Sigma being a Greek letter. The capital version of that letter looks like a sideways M. Okay, so remember that a series is just a sum of the terms that make up a sequence. So a finite series, that's just going to be one that has a termination, a final value, a final term. So remember, S of n is a sum of n terms, and so it's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot dot dot, all the way up to a sub n. All right, so we'll write that with the sigma notation. So we have the sigma, and then we have I equals 1. That is the starting value. So I replace this I in here with a 1. So the first term will be I sub 1. And then I sub 2, and then we increase this one more to I sub 3, and then we do a sub 3, and then I equals 4, then a sub 4, and so on, until we hit the n value, whatever it ends up being. So in our problems, as you see down here, the n will be an actual value, not a variable. So we start at this value, and we plug it into the formula that's here. So we a sub 1. Increase this by a value of 1, add 1 to that, and then we use a sub 2, and we so on and so forth until we get up to, and we use this value up here that will generate the a sub n term. Okay, so that was for a finite series. For an infinite series, the only difference is, first of all, it's the sum of the first, I guess, from 1 up to infinity, the infinitieth, I guess you might say, term, the last possible term, infinity. Seems like an impossibility, but we'll deal with infinities a little bit. So again, we start with I and we go up to infinity. As often this will be a particular value. Remember, it's a sum. So even though you may not be able to write out all those terms because it's up to infinity, the sum of all those terms will have a potential value. Okay, so the I that we use as the sort of the counting number or the counting variable is denoted as the index of summation. Now, it looks a lot like the I that we used in previous chapters for imaginary numbers. It has nothing to do with that. It absolutely has nothing to do with it. It's just the same symbol, but used in a completely different way. All right, sometimes instead of I, we might use J or K. All those kinds of numbers, I's, J's, and K's, all sort of in mathematics indicate that we're dealing with integer values. All right, so let's try an example. All right, so we're going to write out all of the terms and then find their sum. So to generate the first term, or the a sub 1 term, we use this first value, which is 1. We plug it in. So 2 times 1 is 2, plus 1 is 3. So the first value we have is 3. And now we increase the I value by 1 to 2, and we plug 2 in there, so that's 4 plus 1, that's 5. And we continue this process until we've used a 6. Okay, so we have the first term, the second term, third term. I is 3 now, so that's 7. And you can see pretty quickly that this is just going to be all of the odd numbers. Okay, so I is 1, I is 2, I is 3, I is 4, I has a value of 5, and I has a value of 6. And now, how did we decide to stop at 6? Because that number's at the top. It's 6. So when I put a 6 in here, 2 times 6 is 12, plus 1 is 13, so that's the last term. Now, what we have to do is simply add all of these up. That ends up being 48. Okay? Next one. This time we're not starting at 1. You're not always going to start at 1. This time we start at 3. So a sub 3, if you want to think of that, the first term we get that we're concerned with is going to be using an I value of 3. So I put a 3 in there. That's 3 squared is 9, minus 1 is 8. So our first term that we're going to deal with is 8. I'm going to keep going. I'm going to add 1 to it. So now I is 4. So 4 squared is 16. 16 minus 1 is 15. I'm going to keep going until I use the number 8. So let's see. So where are we? So that's 3, 4, 5. So 5 squared is 25. Minus 1 is 24. And then we increase I by 1 more. So it's 6. So 6 squared is 36. Minus 1 is 35. And then we use, what did we say? 7. 7's the next one. So we increase by 1 more 7. So 7 squared is 49. Minus 1 is 48. And then, so that was 7, 8. We increased by 1 more, 8. So that's our last value because that's the number on top. But we actually use it. So 8 squared is 64 minus 1 is 63. And when we add all those up, we get 193. All right. Next one. So we start with an I value of 2 this time. So we put a 2 in here. 2 minus 1 is 1. 1 squared is 1 times 2. And that gives us a 2. I guess I should put an equal sign in front of all these because this thing is equal to this. So this thing is equal to the sum of numbers. So we have, that was 2. We now increase it by 1. So now we have 3. We put 3 in. 3 minus 1 is 2. 2 squared is 4. 4 times 2 is 8. All right. Now the second, third, fourth term now. So 4 minus 1 is 3. 3 squared is 9. Times 2 is 18. So this is the first, second, third. Now we're dealing with the second, third, fourth. Now we're dealing with a sub 5. So I put a 5 in here. 5 minus 1 is 4. 4 squared is 16. 16 times 2 is 32. And so when we add that up, that series is equal to 60. Okay? Okay, so we have some properties that adhere to these the series or summation notation. So if I have the summation, so in other words, if I have a formula that doesn't have an I in it, then every time I generate a term, it's just going to be the constant. So for example, if I is equal to 1, there's nowhere to put I in, so the first term is just going to be a C. Then I add that to the second term. Now I is 2. Well, there's no I in the formula, so the second term is also going to just be C, and so on. That will continue until I have n C's added up, or just C times n. Okay. If I have a constant times a formula, and I'm summing that formula up, I could take the C out in front, and so it's the constant times the summation of that particular formula. That's what part B is saying. And then C says if I have the summation of the sum of two formulas, that's the same as the sum of the two summations individually. And if this is true, it kind of follows that it works well as well for the difference. Okay. And then we have some summation rules. These you really just have to commit to memory. When we do the next couple of sections, this one will make more sense, but you just need to memorize these. So if I am summing up from 1 to n, and the formula is just I, so that means when I is 1, it's 1, when I is 2, it's 2, and I is 3, it's 3, all the way up to n. I add all those up. Instead, what I could do is do n, which is the total number of terms, this n here, times n plus 1, all divided by 2. When I'm adding up the squares, so that would be 1 and 4 and 9 and 16, all the way up to n squared. If I'm adding all those up, then the formula n times the quantity n plus 1 times the quantity 2n plus 1 all over 6 will work. And then finally, when you're cubing each of the terms, so that would be what, 1, 8, 27. When you're cubing each of those terms, that's what the formula is. then you have the formula to find the sum. You can just do n squared times the quantity n plus 1, quantity squared, all over 4, and that will give you the sum. All right, so let's use these formulas in the two boxes above to do some of these problems.
Okay, so for exercise 6, part A, this sort of pertains to this first formula here in part A up above in our summation properties. However, this one's a little bit trickier because it doesn't start at 1, it starts at 4. So we have to think about, okay, so first of all, hopefully everyone realizes that since there's no I in this formula, when I use I of 4, I plug it, well, there's no way to plug it in, so I just get a 12. And then when I put an I increase it by 1, so it's 5, put a 5 in here, there's no place to put it, so it's just a 12. And so that continues, and so we end up with just a bunch of 12s that we're adding up. All right, so what we have to figure out here is how many 12s there are. Well, there's not 40 12s. There would be 40 if we started with 1. So the common mistake is that students just subtract these things and say, well, there's 36 12s. Well, that's not quite right. So think about it. If we started with 1, if we did a summation of 1, starting with I of 1 to 40, well, that's 40 terms, right? So it's not right to just subtract it. 40 minus 1 would be 39. So if that doesn't work here, it seems like it would also not work here. So if 40 minus 4 would give us 36. That's not the number of terms. It's really 40 minus the bottom number plus 1. So the number of terms here, or in this case the number of 12, is going to be the top number 40 minus the starting value of 4 plus 1. And so that is going to be, there's 37. So how would we calculate the sum of those terms? Well, it's simply 12 times 37. Each one is a 12. We multiply by 37 because there's 37 of them, and that gives us a total of 444. Okay? All right, so let's move on to the next problem, B. So B is using this part B up here, so we have a constant times this. So we could rewrite this thing as 3 times the summation from I equals 1 to 35 of I. All right, so we can bring that constant 3 out in front, do the summation of the simpler one first, then take that result and multiply it by 3. So that's using this formula here. So that summation is going to be equal to 35 times 1 more than that, 36, all over 2. And that gives us a grand total of 1890. Okay, next one here, we can break this up. We can actually do this a couple different ways. We break this up using this rule here. And then we can also bring the 3 out in front using this rule here of just that one term. So we're going to do, this is the same as 3 summation I equals 1 to 10 of I squared plus the summation from I equals 1 to 10 of 5. All right, so this one is going to be using this formula. So it's 3 times, and then let's use the formula. N is 10, so we have 10 times, I guess a dot there. So 10 times 11 times 21, all over 6. And then plus, and I think you can see this is just going to be 5 each time. Each term's going to be 5, and there's going to be 10 terms, so that's 50. Okay, that gives us, we work all that out, a grand total of 1205. 1,205. All right, so similar thing here. We're going to break this up using these two formulas here, C and B. This is a difference, so we'll use this thing kind of for that. This is a plus, we'll use this term for that, that formula for that. All right, and so let's do that. So that's going to break it up into, we're going to have the summation of I equals 1 to 10 of I cubed plus, and then we can bring this 2 out in front, 2 times the summation, I equals 1 to 10 of I, and then minus the summation of I from 1 to 10, and that's just going to be, all those terms are going to be 8. Okay, so using our formula, the first one's going to be this. So that's going to be 10 squared, which is 100. And then the 11 squared, 121, all over 4. The next one is going to be 2 times, and we're using this formula now, 10 times 11 over 2. And then finally, minus 8, and there's 10 of them, that's going to be 80. Okay, so that gives us 3,025 plus 110 minus 80 for a grand total of 3,055. Okay, so you have your homework down here at the bottom. That homework will be due next class. All right, don't forget, 8 a.m.